It's really nice to be here and see so many faces of friends, to some of whom I haven't had a chance to say hi, but hi. Yeah, I don't know how many times I've been here, but I think the first time that I talked about globally valued fields was here. It was Jan de Neef's birthday conference, so it's a very, very, well, that's 12 years. This is a really much longer range project for me. I started thinking about it some decades ago after hearing a talk by Lau van den Dries about the algebraic integers, where he somehow, what came out of his talk is that you have to think not of one valuation, but all the valuations on Q bar. And you have a language which doesn't quite tell you what any single valuation does, but globally it tells you what the space of valuations does. And well, this is the algebraic integers. Okay, I'll explain in a minute that it's very natural to complete it. So to take the algebraic integers are missing, they don't know about the prime at infinity. If you take the function field analog, that's like a curve with a missing point. And there's a lot of geometry that you cannot do if there's one point missing, that you only see when you have the whole picture. So it's quite interesting to try to make a model theory out of that. But it has been a very long project. The two main points in this project were when I realized after a few years that this must be done in continuous logic, and discussed this with Itai Ben Yaakov, who then joined me in this project in the last decade or so. And more recently, Michal Shachnievich joined also, and you'll hear, I think, tomorrow a fantastic result that he has on the case of Q bar, on the number field case. Essentially everything I'm going to do today, you can at least think that it's for function fields, that it's for, yeah. Okay, so let me go back. This is a conference on valued fields. So, okay, the most basic example is the field of rational numbers, and we know what the valuations are. You have the p-adic valuations, so you can think of them as embedding Q into QP and taking norm, but you do it additively. And then there's a kind of honorary valuation, which is not quite a valuation, which involves doing the same thing with the real numbers. And what model theory reflects so far is that you may have a bunch of valuations, but they have nothing to do with each other, right? Either you have model theory of one valuation, or you have a finite number, or maybe you have all the valuations in Q, but in model theory, they're completely independent. They don't talk to each other. And in fact, that's what the Chinese remainder theorem in various extensions of independence of valuations, things like that, that's what they say, that there are no relations between valuations, at least if you take finitely many. So, for instance, Chinese remainder theorem says, well, you can prescribe what x should be modulo 2, 3, 5, and 7. There will always be a solution. There are no constraints. And in fact, it goes much further, and this is somehow the basic principle behind the theory of the algebraic integers. Even if you allow all but one valuations, you just drop one, then still there are no constraints. So if you, so when I said you can make something equals to 2, 3, 5, whatever you want, mod 2, mod 3, mod 5, you can get that to be an integer, which amounts to infinitely many other constraints, that the valuation at L should be 0 for all L except at infinity. Or else you could do something else. You could drop the prime at 5 and insist that you should say something about the absolute real value as well. You can still get something with prescribed value at 2, 3, and 7, and quite close to any real thing that you want, right? You just divide by an appropriate power, the power of 5. So they are very largely independent, but not when you take all of them together. So Chinese remainder theorem says they're independent, but the fundamental theorem of arithmetic says they're not independent. If you take all of them, there's one relation. So here's the fundamental theorem of arithmetic, right? So any integer can be written as a product of primes. Well, at least any positive integer, so with absolute value, it's correct. And if I take the log of this, then what I get log of n, which I'm going to move to the other side, so it will become this minus log there. And then log of p will come out as a coefficient, as a weight, and I'll have the valuation of p. So what I get is that these valuations are not independent. They satisfy a linear equation. The only trouble is that this linear equation is not finite. It involves infinitely many things. So you can try axiomatizing it in first order logic, but it's not, well, okay. What's more natural, let's say, is doing it in continuous logic. Yeah, okay, so before saying that, there's the analog for function fields. If you take a curve over an algebraically closed field, evaluation over that field corresponds to a point, and you have to give weight 1 to each point, and then you get, again, the product formula. So now instead of the rational numbers, we have the rational functions, and any rational function has a bunch of zeros and has a bunch of poles, and if you add them up with their weights, so poles count as -1 and zeros as 1, and double poles as -2 and so on, then you get 0. There's many zeros and poles. Okay. Yeah, so actually I guess I'm still going to stay without the model theory for one quick example. So there's a lot of number theory and geometry which depends on this, which is not local, and it's not semi-local, it's not multi-local, it's global. And just to give some very, very basic examples, so there's the theorem, I don't know whose it is, it's kind of like Liouville's theorem that we learn in complex analysis. But anyway, the basic result that you don't have a holomorphic function on a curve. So here's the proof using the product formula. So you have f without poles, so nothing goes to infinity, right? It's a holomorphic function. Then the claim is it must be equal to some constant, and otherwise, then for every alpha, this still has no poles when you subtract alpha. Well, the number of poles is the number of zeros, so there are going to be no zeros either. In other words, f doesn't take the value alpha. But if that's true for every alpha, then, well, it has to take some value. So that's a proof. And a very analogous thing in number theory is the theorem of Kronecker that says that if something has non-negative valuation for every valuation, then it must be a root of unity. Okay? If something has, so here's the proof of that. So you take a finite extension of the rationals, and you have all the valuations of that. Yeah, and now let's look at the set of all elements whose valuation is everywhere non-negative, okay? So in particular, for the complex norm, I mean, it's inside the unit circle. So it's everywhere non-negative, and the theorem says that this is the root of unity. In other words, that this is a finite group. That's what you have to prove. So first of all, as written, oh, yeah, sorry. Somehow, okay, I improved this slide, but I have the old one. Okay, so the first important observation is that I wrote here greater than or equal to 0. But actually, that's the same as equal to 0, because the product formula says if you take the sum over all v, you get 0. So if it's a non-negative function, it must be identically 0. And yeah. Secondly, this mu L, okay, I'm giving a much too fancy proof. There's a much simpler proof using even one place, but let me just say it anyway. So this mu L is discrete by the product formula. In fact, if you look at the topology not given by a single completion but by all of them, then the whole of the number field, the whole of L, is discrete in this topology. So this is what the product formula tells you. You cannot approach 0 or some other algebraic number. Well, you can approach it, of course, in the real topology, or you can approach it in the p-adic topology, but you can't approach it in all these topologies at once. Because if you get too close in all of them, then, okay, then the product formula will be impossible because the sum of positive numbers cannot be 0. Okay, on the other hand, when you take the product of these, so all of these points lie in the, either in the unit ball of the complex numbers, which is compact, or else in the ZP, in the variation ring. So therefore, this is a compact, and you have a discrete subset of a compact space, so it's got to be finite. And it's clear that it's a subgroup. So this is the proof. There's actually a much easier proof using the product formula, which I'll leave you as an exercise, using compactness in one place. But, okay. Okay, so we would like to have an axiomatization of that. And clearly, if it's going to be axiomatized in any kind of first-order way, even a continuous logic way, then you cannot expect to have the same kind of just discrete sum, right? I mean, compactness is going to mean, okay. On the other hand, measures are well-behaved, they're very, and so you should think of it as a measure. So for example, in the case of Q, it gives mass log P to the P's valuation. However, I'm going to avoid any measure of theoretic complexity in this talk. So if you just think of the situation that you have many valuations, each one is assigned some weight, then it should be good enough. All right, here's the language. You can axiomatize it in various languages. The one that I like is very elementary. So you have a field, and then you can think that you have the real number. You just have the real numbers. And continuous logic tells you, well, they don't change under ultra products. They just stay the real numbers. By the way, it's really the real numbers and not just the interval -1, 1. It's not bounded continuous logic. But that's okay. And yeah. Now, yeah, so first of all, we have terms, we have function symbols, and these are just polynomials. And equality is just equality. It's just 0, 1 value. You don't have a metric. This is not a metric. This is not a metric continuous logic theory. It's just a plain continuous logic theory, so you can think the metric is discrete if you want. Okay. But a lot of the complexity of continuous logic goes away. And on the reals, the tropical terms are whatever term you can get in this signature. So you have plus, you have scalar multiplication by rationals, including by -1, which may mean that some tropical people will disagree with me about the term. It probably shouldn't be called tropical. Tropical maybe doesn't have minus, but we do have minus. And you have the minimum function, okay? So it's like taking log of multiplication and addition. Log of multiplication is addition, and log of addition is something like minimum or maximum, like maximum. Yeah. Yeah. By the way, this kind of term is exactly, as far as I understand, it's exactly the kind of thing that you get from a machine like, well, from a neural network machine after it's been trained. That's what it does. I mean, you have a number of layers, and each time either you take a linear combination or you take a maximum. And in fact, first they had attempts which used more C-infinity terms, approximation to this, like will show up in Michal's talk maybe tomorrow. And now they settled on exactly this kind of term. I don't know what it means, but yeah. Anyway, going back, so these are just terms. Now, if you have a valued field, don't think of the valued field as, don't think of formulas saying what is true and what is not true. Think of definable functions into the value group. For example, values of polynomials, values of elements of your valued field, or minima of such values, or various combinations. Okay, think of it as functions into the value group. So we're going to have a symbol IT for each tropical term, and we're going to think of, so the local interpretation in any given valued field is you just apply the term to the valuations. And the way I'm supposed to think of the global interpretation is that, well, it's the sum of these over all the valuations, or the integral with respect to your measure over all the valuations. Okay? So it's not quite correct to say that it's the mean value because it's not a finite probability measure, but it's proportional to the mean value, so to speak. Okay. Okay. And here are the axioms. It's a field. There's some trivial axioms, and this I is linear. And okay, it's non-negative. So if you have a function which is everywhere non-zero, what is supposed to be the integral should be non-zero. And finally, you have the product formula. So this is what we were discussing. The integral of the valuation of x over all valuations should be 0. So in this language, we managed to say it. And in fact, you have a statement that this is the syntax, but but you can think it does capture the semantics that we wanted it to capture. So so if you have a GVF, then it's not quite unique, but anyway, there will be a measure on the space of valuations such that this is the interpretation. Okay. So now here's a theorem towards Micha's talk tomorrow. So GVF, I just wrote down some universal axioms. This is the correct universal theory of the class of global fields, where by global field I meant in the sense of André. So a global field is either a finite extension of the rationals, either a number field, or a finite extension of the rational functions over a finite field. It's also the universal theory of the function fields of curves over all fields. You can either restrict to the finite ones or not, as you wish. So I stated that there's a theorem, but it's really two theorems because there are two kinds of GVFs. Well, they may have characteristic P. If they have characteristic 0, they extend the rational numbers. But which structure on the rational numbers? There are really basically two choices. Either the one that I explained earlier, namely P gets measure log P. Of course, you can renormalize it, and you can give it measure 5 times log P. It wouldn't matter. At least before you take limits, it doesn't matter. Anyway, so that class is captured by, you can look at the, So the maximum valuation of 2, am I saying it right? So the two adic numbers give you valuation 1. So the maximum, So in Q, the height of 2, the integral of the positive part of a variation of 2 over all valuations is going to be log 2. On the other hand, you have the other possibility of thinking of it as a function field. So all of the valuations of Q get measure 0, and then the valuations you're interested in come from, from the function field. And in that case, the height of 2 will be 0. So you have, sorry? It's not.
How can you renormalize 0 into a non-zero number?
No, that's what you can't. So it divides into two cases. One case is the case of 0, and the other case is any non-zero number. And after renormalization, I can take that non-zero number to be log 2 so as to match the usual conventions. Yeah. Okay, so in fact, there are more number field type valuations in some sense, or GVFs, than function fields, they approach, after a certain renormalizations, they approach the function field value, which is 0, but they're all equivalent. But it's very interesting when you take ultra products that if you take them and then, well, that you can get ultra products of number fields to be function fields, but this is not for this talk. Okay, so some questions you can ask if you're a model theorist. Well, does this have a model companion? Is the class of existentially closed structures axiomatizable? And, well, is it a stable theory, or how far are the formulas stable? And what I hope to get to is, first of all, describe, so at the quantify free level, I think we know now that it is stable, and there's a little story behind this, a little apology that I have to make, because 5-6 years ago in Bedlevo, I made a claim that the theory is quantify free stable, and I did carefully say that it was, well, the result seemed to be, well, okay, it's a few days old result, and made it a small t theorem, thinking it was less, well, more modest than calling it a conjecture. But in any case, I was wrong. I mean, I was correct about the statements, but wrong that I had a proof. So there was a big gap in the proof, which I will explain. And yeah, so GVFs, they assign weights to evaluations. And if you have a variety, the evaluations can live on various subvarieties. And what I was saying was correct. It was the correct extension procedure. It was correct for codimension 1 subvarieties, but there was a gap with respect to higher codimension subvarieties. And during the intervening years, I tried to work on it a lot. And first I got the codimension 3 subvarieties, but codimension 2 remained open. Then Karima Di Posito joined, and well, he managed to do the first non-trivial case somehow in codimension 2. There was some other progress, but finally there was a phone conversation with Itai in which he saw the light in a completely mysterious way. And I think he will tell you within 1 second, and I think he will tell you, I don't know when, sometime this week. What? The last one, okay, so there'll be some, okay, some tension to wait for it. Yeah. Yeah, but so this I will not discuss today, but nevertheless, the way the proof goes, or at least one way the proof goes, is the following. If you expect something to be stable, then stable theories, there's a canonical extension of types, right? You have to say something that the base should be in some sense algebraically closed or a model or whatever, but there should be a canonical way to extend types. There should be a canonical way to amalgamate. And if you're trying to show something is stable at the QF level, then one way to do it is to give the canonical extension, okay? That's part of what you have to do. And the second part is to show that this is the stable choice. In other words, that if you take any other thing than the canonical extension that you gave, then in some sense it causes forking. It cannot be repeated indefinitely. You can make a mistake once, but not too often, something like that. And yeah, so the canonical extension does involve something quite interesting in codimension 1, whereas in codimension 2 it's easy to state. You just say nothing. It assigns measure 0, mass 0 to codimension 2 types. But just being able to state it doesn't mean that you can prove that that's a stable choice, and that's what we'll hear on Friday. However, today what I'm going to do is not describe the question of the stable choice, but just describe what is this canonical extension, which we'll see connects to some interesting geometry. Okay, so now I have a choice. I'm going to need to go back to these slides later, but maybe it's not convenient to go back and forth to the blackboard and the slides. Shall I just do them now?
No, you can do them later.
Okay. Sorry?
I mean, it's perfectly legible.
Oh, well, but We don't.
They go up and down the board
Oh,
with these things.
I should use the other side. Okay.
No, I'm saying if you want them, if you want to move the middle boards, you could go to the controls and.
I think it's
Okay.
for the middle board.
Yeah, but these are.
We don't need to see this for the time being. So. Okay. So first I would like to describe what? What? Oh, did it? Yeah. Maybe it knows I'm not so tall. Okay. So before discussing, is this legible? No, not at all. It's all right. I see someone at the very last row saying yes. Yeah. Okay. It's easier like that. Is this okay? Was I speaking without a microphone until now? Yes?
No, it's just now.
Just now?
Yeah.
Okay. Okay, so in the same way that we have for difference fields and for pseudo-finite fields, when you have, okay, so quantify free formulas describe structures, right? They describe a substructure, but it's not enough. You need to know also about finite extensions of that subfield. What is the GVF structure on the finite extension? And you have formulas which are a little bit more. So I don't know, you can call them Galois formulas. Anyway, they describe the quantify free structure on an extension. And I think, I believe that these formulas will be stable as well. What I would like to do is to give a proof of a very limited case of that. So, yeah, okay, so first of all, let F be a GVF, and let K be a finite extension, which is Galois. Let's take the case that it's Galois. Okay. Then there's unique Galois invariant GVF structure on K, extending the one on F. Okay, so I guess if you have a valuation on F and you want to extend it to K, then all the valuations above it are going to be conjugate to each other, and therefore they all have to have the same weight. So you know what the weight is. It should be just the weight of the one on F divided by the size of the Galois group, right? So I'm going to speak all the time as if valuations have positive measure and you can speak of a single one, but there are standard measure theoretic ways to say that even when it's not quite the case. Okay. So there is such a Galois invariant extension, but that doesn't have to be the choice that you make. There are other choices. Yeah. So, okay. So the conjecture is that if you have, suppose you have some GVF extensions. I'm not going to say it in a precise way, and suppose they are independent in the quantifier-free sense, and yeah, but let's say they're algebraically closed. Then the Galois invariant extension to the algebraic closure of K1, K2, so it is the unique stable choice. Okay. So on this one, it's easy to describe the canonical extension that you expect. So we already know how to amalgamate. Let's assume we already know how to amalgamate structures. So we have two, and we amalgamate them canonically. Then you have, so now they're both inside some GVF, K1, K2, but that's not algebraically closed anymore. So in order to deal with these formulas, you have to go to the algebraic closure. And there's now here the canonical way to do it is completely clear. You just take the Galois invariant way. But what you have to prove is that if you deviate from that, then in some sense you cause forking. And I'm going to say that precisely and to give an example, to give a proof of us in a special case. So this is a conjecture, but now I will take the case that K2 is contained in the constants. Okay. So what are the constants? So the constant field is defined as we discussed in the proof of Kroneker's theorem. So it's the set of all x such that, well, let me just write that the valuation of x is greater than or equal to 0 for all v, or maybe you prefer to say almost all v. In other words, the integral of the absolute value of the valuation of x is equal to 0. Okay? So we said this is actually a field. It seems to be a sub. Yeah. Is this okay? Okay, so the situation is that we have the base field F. So F consists of, so I'm looking at the case where this has a trivial GVF structure. And we have an extension to K2, which is still a trivial GVF structure. And we also have one to K1, and this one is non-trivial. You form the join of these two, and you get a lot of finite extensions. First of all, maybe if K1 was not algebraically closed, it had itself algebraic extensions. But even if it was, with the new parameters from K2, you're going to get lots more algebraic extensions. And I would like to say, well, you don't have to choose the symmetric extension on them. But it's like a situation where we have in finite rank model theory. Namely, I'm going to assign a certain energy to the situation, a certain kind of rank, which has to go down every time you make the wrong choice, every time you make the non-symmetric choice. Okay? In this case, the energy will be a real number. It will not be an integer. So there's only after countably many stages, the limit will be attained, and you have to make some argument there also. But in any case, this is the picture that I want to show. Okay. So in order, okay, so yeah. So one way to say what the result is that if K2 is quite large, but K1 is maybe f of A for some tuple A is finitely generated, then there's going to be a countable subfield of K2 such that if you take, there's going to be some countable K2 prime contained in K2, this will be countable, such that if you go for maybe the extension of f of A to K2 prime of A, this extension may not be symmetric, but from that point on, it's going to be the symmetric extension. Okay. But in order to discuss this, I would like to talk about varieties, and I need the notion of a GVF structure on a variety X over a GVF F. So this implies a GVF structure on a variety X. It implies a GVF structure on the function field f of x, but I don't allow every single one. I allow only those that concentrate on hypersurfaces of x. Okay. Such that so let me call it mu. So such that mu concentrates on either vertical or adelic valuations. These are the valuations which are non-zero on the base f. Okay? So there are two kinds of valuations on an extension of f, those that are trivial on f and those that are not trivial on f. If it's non-trivial on f, to study it comes much closer to ordinary valued field theory. Because basically you can take your valuation, which is non-trivial on f, and you look at the extensions of it. Okay, so, and divisorial valuations on x. Okay, so what is this? I always take x to be a normal variety. And if you have a hypersurface H contained in x, so it's a subvariety of codimension 1. So for the purpose of the talk, not to get into technicalities, you can think that it's a smooth variety. And if you take a subvariety of codimension 1, there's an associated valuation. On x, right. So basically, if you have, so here you have x, and here you have your subvariety of codimension 1h, and if you have an element of the function field, so you can think of it as a rational function, and you say what it does at the generic point of h, what it looks like along h. So if it vanishes on h, then you say that the valuation is positive. If it vanishes to order 1, the valuation is 1. If it has a polar for order 1, it's negative 1, and so on. Okay. So you have valuations which are associated to hypersurfaces. Right. So now the condition of being a GVF on x means that among the valuations which vanish on F, the only ones you can see correspond to subvarieties of X. Okay? So it's a very special class of GVF extensions of the function field, but we do have the GVFs on the function field. It's exactly a projective limit of GVFs on X or blowups of X, such that. Okay, if X is a curve, then it's just on X, but if X is a higher dimensional variety, the function field doesn't determine the variety. You can blow up points or ideals and get other varieties with the same function field. And if you know about GVFs on X prime for each such X prime, then you basically know about GVFs on the full function field. So even though this is a very special class, when you study all of them, it's not substantially different than studying all GVFs. Okay. And in particular, if you have the special case where F is trivially valued, then it's just these valuations. Okay, so it's quite similar to the case of Q or the case of K of C for C a curve, namely, okay, you just concentrate on codimension-1 things. You give them a certain mass. In this case, yeah, you're welcome to think of the base field as countable, and you're going to have countably many such subvarieties, and therefore such measures are automatically atomic, right? I mean, okay. They give some positive mass to some hypersurfaces and not to others. Okay. Right. Okay. So what? Okay. So now take F trivial, then GVF structure on X is the same thing as taking a map from all divisors, so on X. So these are formal combinations of hypersurfaces on X into the reals, such that what? Well, it's going to be linear. It's going to be positive on hypersurfaces. So people say effective divisors. In this, in the formal divisors, we add negatives also. We take formal linear combinations, but if it comes from a measure, then it should be positive on effective divisors. And finally, it should take, if you have a rational function f, then the divisor of f, so all the zeros of f minus all the poles of f, that must go to 0. Okay. Well, it's not the same. Yes, thank you. Okay, so in other words, so there's only one of these here. Yeah. Is there one? Oh, yeah. Thanks. Okay. Okay, so therefore, GVF structures on X is the same things as homomorphisms from, well, so this is called the Picard group of X into the reals, and you have to say that they are non-negative. So, well, which preserve also the effective divisors that take a hypersurface to something greater than or equal to 0. This is just a restatement. The Picard group of X, by definition, is the divisors divided by these principal divisors. Okay. So what I would like to do is associate to such a structure a certain number called the energy, such that if I go to a finite extension, the energy and I don't take the Gauss symmetry. If I go to a finite extension, the energy either stays the same or goes down, and it stays the same for the unique extension, which is Gauss invariant. And I will just do that for this talk for the case of surfaces, for the case of dimension 2. So I'll need some information. Yeah, so.
Do you want to switch back?
What? No, I don't want to switch back yet. Should I? Until when am I talking?
At 5:02.
5:02, but
15 more minutes.
Oh, really?
Yeah,
Okay,
you started at 5:02. You get 1 hour.
I see. Okay, fine. No, I was looking for something to erase. Yeah, okay.
So you're talking about extension to the algebraic closure, right?
Yeah, but I can do it one step at a time. So I'll talk about an extension from X to a finite cover of X.
But did you explain what is the structure on K1, K2?
It's given. I mean, there are some given GVF structures. I don't know what they are.
No, like on the product.
On the product, no, I didn't explain it. I mean, if I have time to go back to the slides, I will explain it.
You still have an empty board. Behind, in the middle, there's 3 boards.
Okay.
If I'm not mistaken.
But you need to raise the first two.
Okay.
You use the buttons
What?
to raise them, because otherwise you destroy the machine.
Oh, really? It didn't feel like I was destroying anything.
Well, you saw that the third board had a tendency to go down, and that's exactly because of that.
No, it went down when I was using the buttons as well.
So you're saying you're not the first one to not.
I see. Okay. Okay, so I need to bring in a few facts from geometry. And so this is part of the point to kind of show what kind of structures from geometry we intersect here. And I'm not sure anymore I'm going to get to the abelian variety part. To describe the quantifier free types, you need these abelian varieties. And they're kind of familiar to model theorists for many things, but in particular from the study of differential algebra, where they also play an important role. But here, into this finite extension business, there will come a kind of geometry that at least I've not run into before in the interaction with model theory. So I need to describe it a little bit. Okay, so here are some facts from geometry. So first of all, yeah. Okay, so the Picard group of X contains a kind of continuous part, which is called pic 0, and phi, I'm not going to prove that here, but phi has to vanish on pic 0 of X. So pic 0 of X is when you have a whole family of divisors, you take the difference between any two of them, that's an element of pic 0. It's the part, those that are algebraically equivalent to 0, and that can be large. That, it turns out to be an abelian variety, it's a variety, and if F is a large field, this can be a large set. But the quotient is called the Néron-Sévère group of X, so it's pic of X divided by pic 0 of X, and this is always a finitely generated group. So if you take this, it's a finite dimensional space over the real numbers. Okay? So this is the theorem of Lang and Néron that this space is always finite dimensional. The second statement is that there is an intersection theory on X. So you have a bilinear map from ns of X into the reals, so it's bilinear. And it's uniquely determined by the fact that, so here's X, and if you have two, let me state it for curves now. So now X is surface. So if you have two curves, C1 and C2, yeah, this then C1, so these are hypersurfaces, so they represent elements of the Nolan-Severi group, and the formal product of C1 and C2 is in fact going to be the intersection, the size of the intersection of C1 and C2, provided that they meet transversally, if they're not tangent to each other. If they are tangent to each other, you just have to say the same thing with appropriate multiplicities. So there's one case which is mysterious. This almost gives you the full structure, right? It's not, it makes the theorem trivial, but it's not trivial because of the case C1 equals C2. If C1 equals C2, you don't know what to do. So what you have to do is to take another C1 prime, which is equivalent to C1 in the Nolan-Severi group, and take the intersection of that, okay? But intersection theory tells you that this is well defined, that it doesn't matter which other representative you take, and so on, okay? So there is such a thing. There's a bilinear map which gives you intersection theory, and it's obvious what it is almost always, except in the diagonal case. That is going to make the next fact surprising, so that's 2. And the additional thing I need is the following. You see here we have a vector space over the real numbers with a bilinear pairing, which is obviously symmetric, right? So if you study linear algebra, then the obvious thing to ask about it is what is the signature of this form? First of all, it's non-degenerate, but you can take that to be by definition if you want for these purposes. It's not actually, I mean, it's a non-trivial theorem, but if we could do it here, you could just factor out by the kernels. But the next fact is the Hodge index theorem, which says that the signature is plus minus minus. So it has a certain dimension, and it's going to be the direct sum of a one-dimensional positive definite vector space with the rest of the dimensions a negative definite intersection. So this should be surprising, right? Because the way we defined it, you only see on the non-diagonal terms of the matrix, you only see positive entries. But nevertheless, when you take into account the diagonal terms, you see only negative things. So this was proved using complex methods by Hodge, following Lefschetz, and Andre Weil proved it for products of curves algebraically because he needed it in characteristic P. Because when you say that for product of curves, it basically, it's equivalent to, it gives you the Riemann hypothesis for curves. It gives, so he wanted to count points over Fp of curve, and you go to the product of the curve with itself, you express the points as the intersection of Frobenius with a diagonal, right? So now you're over an algebraically closed field and you're doing intersection theory, and this sufficiently determines the nature of the intersection theory to give you exactly what they wanted. And then Grothendieck generalized this algebraic proof to arbitrary surfaces. You can state it also over arbitrary varieties, but really the case of surfaces is the heart of it. Okay.
Can I ask a basic question? Why is
Yeah.
it valid in the reals, dividing in form for the intersection theory? Why is it valid in the reals and not the integers?
It is valued in the integers, but for our purposes, since anyway we're going to be interested in homomorphisms from it into the real numbers,
So you basically
I'm changing the scalars to the, yeah. Thanks. Okay, so now I can give the proof. Oh, I shouldn't do that, right? Yeah. Oh. Yeah, when I was young in Jerusalem, there was a kind of slogan, every talk should contain at least one proof. And people would say, okay, now I'm giving the proof, and there's the proof. And today I think the slogan is almost something like, no talk should contain more than 0 proofs or something like that. But I'm going to give a proof. It's very easy. Okay, so we have x, and we have a GVF on x over f. So it's a linear map from an S of x into the reals. And because the intersection pairing is non-degenerate, you can just write it as mapping D to D intersection with Q, right? There's going to be a unique Q like that. In a minute, yeah. Okay, you see this Q is unique, so the energy is by definition Q squared. Does that make sense? It seems to be, in any approach to this theory, it seems to be very, very essential to use duality, but not to use it as a formal device, but also to use, if you just use duality, if you had 2 separate vector spaces, there would be D times Q, but there would be no sense to Q times Q. Here it's important also Q times Q. You look very puzzled, but why?
Is it Q less than or Q?
What?
Squared, okay.
Yeah, sorry, so yeah. Okay, but yeah, I forgot to say it, but I need actually one more theorem. So there's a theorem of Kleiman. Since Q times E is non-negative for hypersurfaces E, so for, okay, let's say curves E, Q times Q is greater than or equal to 0. So this is a non-trivial result. You see, I described to you completely the vector space with the intersection form, right? Is it? Yeah. But that's not the whole structure. What?
What is Q?
Okay.
What object?
So we had an intersection theory. Given 2 elements, you get their product, and it's non-degenerate, so there must be some unique Q that does this.
So X is a surface?
X is a surface, yeah. So it's considerably more complicated in the non-surface case, even though it does eventually reduce to surfaces, but I didn't give anything about the reduction. Yeah.
And actually it's not integer anymore.
It's a real number, yeah. Okay. I guess there's no. I'm aware, yeah, yeah. I'll try to give my proof in 1 minute, yeah.
Well, you have to deduct the time for the bullets to go up and down.
But from what
Yeah.
we deduct that from our numbers, or?
Then she's at plus 30. I mean, we can calculate the calculation.
Okay, so now we're almost done to prove this kind of stability for this kind of formula. Namely, now we've assigned an energy to a GVF structure on X, and we visualize a finite cover Y. So it's, okay, so it's another variety of emitting a finite morphism to X. And it also has an energy, and what has to be shown is that the energy of Y is at most the energy of X, and equality in one case only. So it's going to be really an exercise now. Okay, so the symmetric case is what is the Galois symmetric case. So these are GVF structures. The Galois group acts on that the Galois group preserves the GVF structure. Yeah, that the Galois group. Let's assume that Y is a Galois extension of X. Then there's a Galois group acting on it, and it should preserve this structure. That's okay. So if you go to the function field, it's what I described before, that it's the Galois invariant extension. Okay, so Uy is given by D maps to D times Q prime, where mu x is given by D maps to D times Q. Now, the Néron-Severi group of X embeds into the Néron-Severi group of Y. I can think of it as a subgroup or subspace, because if I have any hypersurface on X, I can just pull back, maybe to get a reducible one, maybe irreducible, but anyway, I get back something on Y. Okay, so yeah, so I can write Q prime as Q plus some error term. What should I call the error term? I called it, well, okay, plus alpha, right? Q prime, so alpha equals 0. If alpha is equal to 0, then it's a uniquely determined case, and it's clearly Galois invariant, right? It's canonical. So we must show that alpha is less than or equal to 0, and that it's equal. Okay, and yeah. Okay, so let's compute the energy. So this alpha is orthogonal to anything coming from the Néron-Severi group of X. Because Q prime, if you have something which is in the Néron-Severi group of X, then D, let's call it D, then D times Q prime should be equal to D times Q because it's a GVF extension, right? So therefore, alpha times D should be 0. Okay, so these are orthogonal, and yeah. Now here, in the Néron-Severi group of X, you already have an ample divisor A. This means that it's the pullback of a hyperplane from some projective embedding of X. And this ample divisor, when you pull it back by a finite morphism, it stays an ample divisor. So maybe that's another theorem of Serre that I should have quoted. So in any case, alpha lies in negative definite part, and yeah, now I can just make my calculation that Q prime squared is equal to Q squared plus 2 alpha times Q. That vanishes because we said alpha was orthogonal to Néron-Severi, plus Q squared, alpha squared, and we said alpha was less. We said this was negative definite. It's orthogonal to an ample divisor. So, yeah. Okay, I'm done.
Thank you very much. Are there any questions, comments? Yeah, Noah, can you speak loud enough? Or
I will try. The thing is good here, the variety, if you take the function fields on the variety, if you take other PDF. Now, the way you said, you take the non-trivial ones, and which means that on F they would be independent, non-trivial, right?
So, what do you mean by independent? Oh, what? What do you mean? So, okay.
What would be on F? The constant thing. What would happen?
For what I proved now, F was trivially valued.
You did take only the trivial.
I took the base to be trivially valued, and even one of the sides of the analog to be trivially valued. Yeah, that's why it's not the whole conjecture on the Galois invariant formulas. It's just a bit.
But what if you want to take the non-trivial?
Yeah, I can. If you want to take the non-trivial ones, then it's okay. First of all, I don't know how to do the case of Galois formulas in that case, even though maybe it's close. On the other hand, just for quantifier-free, already in that case, already the quantifier-free canonical extension is non-trivial. And what you do is the following. If you're looking at a specific valuation of F, then the measure above that is just a measure on the Berkovich space of this valuation over F. The simplest case would be that, okay, let me give you the simplest case.
Exactly what I was thinking, because if you take the stably dominated guys, you can also look at them exactly as elements here.
Exactly.
So take the evaluation here that point when point is a realization.
Yeah, so I didn't talk about that, but that's right, exactly. So the canonical extension from Berkovich spaces is a theorem of Poinon, and there's a treatment by Tai, and there's also a treatment by François Lézère and myself, where exactly we view Berkovich points as just ordinary types in ACVF, but such that they're stably dominated, they're generically stable, and then by definition, they have a canonical extension, and if you have a measure on them, that still gives you a canonical extension.
And for RCVF?
I don't know.
Could you give later the references?
Yeah, I'll try, yeah.
Thank you.
yeah,
So does that, for the definition of the energy, if X is not surface, is it just like Q to the definition of X, or is there some?
Yeah, okay, so things become much more complicated in general when X is not a surface in particular. So one theorem, that basically two ways that I'm aware of to represent things. One way is that you take D, so now it's not a surface anymore. Well, you can take it to D times Q to the n minus 1. Okay, this is the basis of the proof of existential closedness, actually both in some sense for Q bar and for function fields, pure function fields. Once you do that, it's not linear in Q anymore, obviously, and you have some convexity theory and it becomes non-trivial. For this particular proof, I was doing something else. I was taking D times some ample to the n minus second power times Q. And so the definition of the energy becomes non-unique. It becomes dependent on the choice of ample divisor, but it still works. And I think it's interesting to compare the different choices, and I think they're not too far. I mean, they give somehow, it's like different metrics on the same topological space. But in that case, there's an additional choice for the energy. Yeah.
Yes, very stupid question, but what's the energy of P2?
I think, so P2, you have to say which GVF structure on P2, right? So maybe you have in mind P2 where you take a line in P2. Yeah, so one way to think about these things, I didn't make the picture, but you have the variety, and to each hypersurface you have to assign a number, right? And the way you can view it is that secretly there's another curve that you're not aware of, and this number is the intersection number of that curve with your subvariety. So if you take the line, it would be the self-intersection of a line in projective space, right? The GVF structure is given by a line, so the energy is given by the line intersects with the line, but it's actually another line, so it's a point, so it's one. Yeah. Yeah, no, it's a good example.
Yeah, so then when you do any color extension, then you get the energy is going to go down.
Yes, if you don't take the symmetric extension, yeah.
Okay, so I'm afraid we need to stop here. We'll have a short break for the minimum of 5 minutes or how long it takes me to wipe the board. And then we resume.